Okay, so I'm just going to walk through this, what this would kind of look like on a wing. Um, so let's look at a traditional wing, and actually let's just start off with a Hershey bar wing here. So here's our center line, and I'm going to change this to white. And we have some definition for ailerons. Okay, so we've got an aileron on both sides, and this is supposed to be symmetric. I haven't drawn it perfectly symmetric, but anyway, it's a symmetric wing. And so we're given some information about this wing. So we're given this z over b location for the beginning of the aileron. We're given the z over b location for the end of the aileron. So those are two things that were given. So I would call that like begin z over b and end z over b, right? So this is my end one, and this is my begin one. We're also given the flap chord fraction for the aileron on both ends here. So we'd have a begin c f over c, and an end cf over c. So that cf it's actually written c sub f over c. That's the flap chord fraction by definition. So this is just a percentage of what this length is compared to the entire chord at that same location. Okay, that's what cf over c is. It's just a percent of the chord that is a flap. Okay, so these are usually somewhere around 20%. Okay, for a lot of aircraft. 15 to 30%, I guess, is kind of a normal range. So, okay, so then we have these different, we've set up our wings. So we're looking at, we're using lifting line theory, and we have these places here that are cosine clustered, these spanwise location. These are the nodes. So these are the nodes along the wing. And so what we need, so the user put in this definition for the flap geometry, but it's actually only going to influence our solution for anything that lies along one of these nodes of locations that we're looking at along the wing. Okay, that's the same with the geometry as well. We only know the geometry, the chord at those locations, and we're using lifting line theory to solve for the lift distribution by making it match at end locations along the wing, that I've drawn here in green. So really all we care about is the CF over C at each of these locations in order to solve the influence of the aileron. So we're not going to capture what's happening in here between locations. This aileron could extend a little bit further out over here and not change anything about the way that we're modeling this. Now, of course, we're looking at this first with very few sections along the wing, but eventually we crank this up to like 50 or 100 sections along the wing to get more accurate results. And what that does is it allows us to more accurately capture where that aileron begins and ends. That's one of the many things that having more nodes along the wing allows us to do. So, in order to compute our chi vector, you remember chi depends on the CF over C at each location, right? So we need to figure out what the CF over C is for each of our nodes of interest here, okay? So let's zoom in on this problem. And I guess for starters, we could think, well, hey, if we've got a rectangular wing and if I'm given a beginning and an ending CF over C, then I could just linearly interpolate between there, right? If I know the Z over B locations of each of these guys. And so I could just linearly interpolate. So if we were going from like 15% to 20% there, then maybe this would be like 16%, and that would be like 19% or something like that. This would just be a linear change in CF over C, right? So let's look at a couple different cases. So one would be like this rectangular wing, and if they gave an inboard CF over C and an outboard CF over C, something like that, then we could linearly interpolate for any location along the wing that we wanted the CF over C, right? That's actually also true if we had a tapered wing. So let's say that we have a tapered wing that looks like this. Remember, the chord is straight, so I've tried to draw that kind of straight here. And we're given some beginning CF over C and some ending CF over C. We can, because our geometry is changing linearly, we could also we could use linear interpolation between those to get the CF over C at any inboard location, right? And of course, outboard of that, our CF over C, we just set that to 0. So our chi vector is 0 outboard of the aileron, right? Okay, so the tricky part here is that linear interpolation only works if we're working with a rectangular wing or a tapered wing where the plan form is changing linearly. In general, and the example problem that you're asked to look at is an elliptic wing. So let's draw half of an elliptic wing here. So it comes out like this. Here's our chord, and then it comes like this. So I've kind of exaggerated a little bit, but and now we're given some root CF over C, and then we're given some tip CF over C there. Now, if we just linearly interpolate the CF over C, what happens is we're going to end up with aileron distribution that looks something like that. But that's not really practical, because in order for this aileron to rotate, it's got to have a straight hinge line. Okay, so what we really want to know is what's the CF over C at every location that would make this a straight hinge line so that aileron actually could rotate. Okay, does that make sense? And to do that, we can't just use linear interpolation between these two CF over C values. We've got to do something a little bit more sophisticated. Okay. So is everyone following me? I can see just a couple of you, but I guess I'm just looking for some nonverbal feedback. You guys following what we're talking about here? Okay. Okay, let me get the chat window open in case you have any questions. You can drop them in there, or you interrupt me as I'm going along here. Okay, so any ideas? How are we going to do this? We know the CF over C to start, and we know the CF over C to end. How are we going to compute the CF over C at intermediate locations? You know, any of these locations where we've got a node from our lifting line algorithm. Any ideas?
I think Daniel in the chat did it with having finding the equation of that line using point slope form.
Okay, exactly. So we can draw a line. We can actually figure out the location of this in 2 dimensions here and draw a line through it, and then backwards solve out what the CF over C is at each of those locations. Okay, so let's just walk through that process. So I'm going to put a coordinate system on top of this drawing here, and let's zoom in on it. Okay, so I've got a coordinate system, and you know, it doesn't really matter how you do this coordinate system. Well, let's try to keep it the same as the way that we've plotted this wing previously. So this we're going to call this Y, and then this we're going to call X. Now remember, now we've plotted the geometry of this wing, so we know what it looks like, and we did that on an XY plot. And so in this X direction, this is really Z over B, right? That's what I'm plotting there on the X-axis, and that goes from 0 at the root. So we'll put in 0 here. That goes to 0.5 here at the tip. That's actually Z over B, right? And then in the Y direction, what we have is we plotted the chord distribution for this wing. And what we did was we said up here, this is always 25% times my local chord, so 0.25 C. And then down here, this was minus 0.75 times C, or the local chord, right? And so I knew the chord. See, I had an array we have an array of arrays of information here. So for example, we have Z over B, and that's an array. We know that at n locations along the wing. We also know C over B, and that's at n locations along the wing. So those are at the same locations, right? So we know that the Z location and the C over B location. And so what we did here was we just plotted 0.2 times C over B and 0.75 times C over B at each of those locations and connected the dots. And that created this, if we just put in some dots here for each of the locations that we know that at, and actually they should be coincident with these green lines. But anyway, we connected the dots and created the outline of our wing, right? And then we could also put in these vertical lines at each of these locations, these green vertical lines, because those are locations where we know the information. And so it just helps us visualize how we've kind of divided up this wing for to solve it. Okay, so in this framework here, in this X and Y coordinate system, we can compute the location of this guy, of this node right there. And what we have to do though, see, we were given some distance out here. This was called I'm just going to call it Z over B 1, or that B shouldn't be subscripted. What's a good? We're going to call it ZOB, Z over B 1, okay? Z over B 1, so that's the location where this aileron starts. Well, I don't necessarily already know the chord there because I don't necessarily have a vertical line here. It's not necessarily already in this array of Z over B's and C over B's that I have. So I need to compute the C over B. So I'm given Z over B1. So I need to also compute the C over B. I'll just put in a dashed line here. I've got to figure out what C over B is at Z over B. Well, if it's an elliptic wing, I can do that math. If it's a tapered wing, I can do that math. However this wing is defined, I can do the math to figure out what C over B is at that location, right? And then if I wanted to, so we're going to call this C over B1. We're going to call this COB 1. That's C over B1, right? And then I know where the trailing edge is of that because I do just minus 0.75 times C over B, and that gives me that location. And then I can subtract off the CF over C1. So we're going to call this guy CFC, CFC1. That was also given to us. So this location right here, the coordinates of that are Z over B1, that was given. And then it's going to be C over B at that location, C over B1 times minus 0.75. And that gets us to the trailing edge plus CFC1. That brings us back a certain percentage of C over B. Does that make sense? So that gives me that point right there. This is the location. Let me finish my brackets there. So that is, I'm just going to call that P1. It's whatever they put in for Z over B, which is the beginning of my aileron. That's the location there in the X direction. And then in the Y direction, it's minus 0.75 times the local chord. And so I've got that right there. Plus the CF over C times the local chord. That brings me back in this direction. Now I just combined the 0.75 and the CF over C and brought the local chord out front, C over B1, okay? So now we found that location there, that in our XY coordinate system here, okay? So we can repeat this entire process and find point 2 by simply using all of the information that was given to us about the tip location. So we're also given C over B, or excuse me, this is CF over C. So I'm going to call that CFC1. We are also given, let's see if we draw a line all the way over to the tip. This is called Z over B. I'm sorry, this is 2. So Z over B2 and CF over C2. So this is the information at the tip. And of course, I'm going to need to compute the local chord at that location. And so I'll call that C over B2. Okay, so from that information, I can compute the location P2. So P2 is just going to be Z over B2, comma C over B2 times minus 0.75 plus CFC2. Okay, so I now have 2 points, and I can draw a straight line between those 2 points, right, in this XY coordinate system. Okay, so I don't know that equation off the top of my head, and just so that I don't give everything away, let's just say that there's an equation. If I have 2 points, there's an equation for how to draw a line through that. Okay, so I'm going to come up with some equation, and I can from these two, I can come up with the equation for a line, and I can put that in the form of y equals mx plus b, right? So that's a point intercept or what, slope intercept form there, right? So I can put that in that form there. And now I can compute the value of this equation at any z over b location. Now x really here is z over b, right? That's what we're using. That we already talked about. Those are equivalent here, x and z over b. So really this is y equals m times z over b plus b. And I shouldn't be using a little b here. That's confusing. That's a span. So let's use a big B. Let's see, I'll get rid of that. Okay, so some slope times z over b plus capital B here, right? So this is just a slope intercept form. Okay, so now I can come back in any time I need to know the z over b at some location. So let's say we've moved on. What we're eventually going to do is we're going to come up with a chi vector, right? Chi, and it's going to look like this, and we're going to have to compute chi at all of these same locations, right? So at any of these z over b locations, we can now compute what we need to do is compute chi. And so what I'm going to do is plug that z over b value at any one of these locations. I'm going to plug that into this equation here, and it will tell me what the point is, what the location is of interest here, right? So let's look at this guy right here. Let's say that we're working on this location along the wing, and so that equation down there, my slope intercept equation, gives me this point. All right, if I plug that in for z over b, so I've given it the z over b location, how far out I am along this axis, and then that equation is going to tell me where that point is. So now I have we'll call this p. From this equation, I'm going to get some p, and let me come back up here. We're gonna call this point P. Okay, so we know where that point is. That's a function of z over b, and now we need to use that information to back out what the local CF over C is, right? Well, we know how that point has an x and a y coordinate, so I'm going to call that z over b, comma, and then some y value here that we got out of that. So so that y coordinate is related to CF over C somehow. And actually, it's related to CF over C just how we got it in the first place at the other locations. So we can use the same relationship with this new y value and solve for C over B at that, CF over C at that location. So let's just rearrange this equation here. So we have y is equal to C over B at any location. Now, this equation that I'm referencing up here, we are looking at it at point 2 specifically, but this relationship holds in general. So it's going to be y equals C over B times minus 0.75 plus CF over C at that location. Okay, so that's what the y coordinate is. So we know C over B at this location because that we already computed right here in this array of all of these locations that we're interested in. We already know C over B. 0.75 is just a constant. So we can solve this equation now for CF over C. So, so the local CF over C is just equal to, let's see, we can just solve this real quick. So it's y over C over B plus 0.75. Did I do that right? So that's my CF over C at any location now along this wing. So I can compute my CF over C at any location here. And then that information is going to feed back into, is going to go into this chi vector. Now, of course, CF over C is 0 for anything outside of this. So we're going to have to first check and see if my Z over B location for any one of these nodes that I'm interested in is within this range here, right? So I'm going to have an if statement in there that says, you know, if my Z over B location is within the range of this aileron, and I know where it starts and ends because I was given Z over B1 and Z over B2. So if my point of interest here is within this range, then I need to compute this CF over C. Otherwise, I just set it to 0 within that chi vector.